Hi, welcome to my presentation. I'm Bo Huang. I work at CIRES and NOAA OAR GSL lab. Thanks for giving me the opportunity to present our recent work on assimilating aerosol optical depth retrievals from VIIRS to improve global aerosol forecasts in NOAA's GAPS aerosol model. The results presented here are based on our recent near real-time experiments. First, I would like to thank all the co-authors from CIRES and NOAA labs and Joint Center for Satellite Assimilation and State University of New York at Albany. We would also like to acknowledge NOAA OAR WPO Air Quality Program for their support and funding on this project. Here is some background information. The NOAA's Operational Global Ensemble Forecast System aerosols, GAPS aerosol, relies on the FRE3 dynamic car and GFS physics. The aerosol parameterization is based on the GODAR chemistry aerosol radiance and transport GOCART model. There are a total of 15 aerosol species in this model, that is, dust and sea salt with 5 size beams, hydrophobic and hydrophilic black and organic carbon, and sulfate aerosol species. It includes a lot of physical and chemical processes, that is, emission, advection, convection, diffusion, dry and wet deposition, and chemical reactions. Both natural and anthropogenic emissions are included, especially daily updated blended global biomass burning emission product, GBBPX, and fire radiative products are used in the model. In the recent, an ensemble variational aerosol data assimilation capability has been developed within the joint efforts for data assimilation integration, which is led by the Joint Center for Satellite Data Assimilation. Our initial results suggest that assimilating aerosol optical depth AOD at 550 nanometer is able to improve the aerosol forecasting in NOAA's GAPS aerosol model. The figures on the right compared the AOD from NASA Marrow 2 reanalysis and the 6-hour forecast without AOD data assimilation on the top, and the analysis with the AOD data assimilation in the bottom. So you can see that analysis with AOD data assimilation is able to significantly reduce the AOD bias compared to the 6-hour forecast without AOD data assimilation. In the most recent, we set up a near real-time experiment at NOAA OAR and GSL. This will give us a chance to more comprehensively evaluate this system. So in this presentation, we will focus on the near real-time experiment results. This is the workflow of the JEDI-based global aerosol EUMETSAT data assimilation system. Like the general EUMETSAT data assimilation system, it consists of 2 major components. The first one is the EUMETSAT component, which runs one control forecast and produces one control analysis after the EUMETSAT update. The second component is the INKF component, which runs a key member ensemble forecast and produces key member analysis after the RTKF update. And a recentering procedure is further applied on the RTKF analysis and the EUMETSAT analysis. To integrate the aerosol data assimilation capability in the JEDI-based EUMETSAT data assimilation system, we first pre-process the AOD retrievals into the IOTA format, which is the observation format used in JEDI system. And we then developed the AOD forward operator and its adjuncts in the UFO component of JEDI, which is further used in the RTKF and EUMETSAT update. In this work, we're going to assimilate AOD retrievals at 550 nanometer from various instruments on board NOAA SNPP satellite. AOD is a column integral type of observations. It represents the total aerosol extinction of solar radiation over a whole column. It can be expressed as a summation of aerosol mass mix ratio multiplied by its extinction coefficients and model layer depths. The left animation shows an example of the NOAA SNPP VIIRS AOD coverage every 6 hours. That's about 1/4 of the whole globe. By following the above equation, all the 15 aerosol species in GAPS aerosol model will be used to simulate the AOD. The resultant AOD increments will be used to further correct the aerosol mix ratio of the whole model layers. In our data assimilation step, the AOD bias and uncertainty is linearly dependent. The value of AOD itself, in general, over land, it has larger AOD bias and uncertainty compared to the ocean areas. This slide compared the AOD forward operator calculation using NASA lookup tables and the lookup tables from CRTM, which are available in the current JEDI-based aerosol data assimilation system. The top figure shows an example of the observed AOD retrievals, and the bottom 2 figures shows the simulated AOD from the CRTM lookup table on the left and the NASA lookup table on the right. So you can see that in general, NASA lookup table shows a much better AOD estimate compared to the CRTM lookup tables. It is likely because that in the NASA lookup tables, it includes the non-spherical dust particles and it accounts for relative humidity's effects on radius growth of hydrophilic aerosols. In our experiment, we are going to use NASA lookup table to calculate the AOD forward operator. Our initial examination shows that our current system has very low ensemble spread, which will affect the performance of the system. So here we developed the stochastic perturbed emissions based on ECMWF's SPPT scheme. Here the SPE, the stochastic perturbed emission, SPE, serves for two purposes. The first one is to scale the emission, which will help to correct modeled AOD bias and increase the background ensemble spread at the same time. In the current gas aerosol model, there are four major aerosol emissions, that is, dust emission, anthropogenic emission, wildfire emission, and sea salt emission. To define the scaling factors, we compared the observed AOD retrievals in red bar and simulated AOD in green bar over different regions where particular emission will dominate. For example, the North Africa is selected to determine the scaling factor for dust emissions. By scaling all the emission by a factor of 2, its resultant simulated AOD in blue bar in general shows much better agreement with the AOD retrievals. The second purpose of SPE is to perturb the emission to increase the background ensemble spread. By comparing the IMS error and the spread from the background ensemble in light green and dark green bar after we perturb the emission with a standard deviation of 2, the resultant IMS error and the spread in light blue and dark blue has a much better agreement consistency. We further tested the STE in our safety experiments. In this bar plot on the right, by comparing the orange without applying SPE and the pink bar with applying the SPE, you can see that SPE is able to improve the fitting of the 6-hour forecast and analysis to VIIRS AOD at 550 nanometer, which is related to its improved background error and spread consistency by applying the SPE method. So in our near real-time experiment, we're going to further tune the scaling factor and perturbation standard deviation for the SPE method and further examine its impact on the data assimilation. This slide shows our NRT experiment design. We performed 6-hourly assimilation of AOD retrievals at 550 nanometer from various instruments on board NOAA SNPP satellites. And 3D INVAR and LRTKF are used to update aerosol species. LRTKF analysis is recentered around INVAR analysis. NASA lookup table is used to calculate AOD forward operator. For computational considerations, the meteorological variables are not directly updated in our data assimilation step. Instead, they are corrected by adding regraded increments from operational GDAS analysis. And we run one control plus 20 member ensembles at a resolution about 100 km using gas aerosol model. And our evaluation will be performed for the period of July 9th to August 17th, 2021. And we have two cycle experiments. The first one is the no DA experiment. That means there's no AOD data assimilation performed. The second one is a DA experiment, which will run AOD data assimilation with a 20-member ensemble. And also in the DA experiments, we applied the SPE method. After our initial tuning, we set the dust and sea salt emission scaling factor to 2, anthropogenic emission scaling factor to 1.5, wildfire emission scaling factor to 1.1, and all the emission perturbation standard deviation is set to 2. Here are some results. This slide compared our cycle experiments results with two sets of independent AOD retrievals. The first one is a NOAA 20 VIIRS AOD retrievals in the top, and the second one is Aqua Modis AOD retrievals in the bottom. The bar plots here shows the globally averaged bias and IMS error for no DA 6-hour forecast and DA background and DA analysis. So you can see that assimilation of AOD retrievals is able to efficiently reduce the negative bias and errors of the simulated AOD. Also, you may realize that the DA analysis shows relatively larger bias compared to the DA background. Our further inspection shows that in the DA background, there are relatively larger positive bias over the dust regions, which further reduce the overall global average bias in the background. It also suggests that our current scaling factor for dust emission is likely too large, needs further tuning. The scattering plot on the right compares the background ensemble spread on the x-axis and RMS error on the y-axis. By comparing with NASA 20 VIIRS AOD, it shows a very good error and spread consistency. However, comparing with Aqua Modis AOD retrievals, the system still shows relatively low spread. We also run some initial evaluation by comparing with independent AeroNet AOD at 8 wavelengths as shown on the x-axis in the bar plots for bias in the top and RMS error in the bottom. You can see that in general, assimilation of VIIRS AOD at 550 nanometer is able to improve AOD agreement with AeroNet AOD at other wavelengths in terms of both bias and RMS error, except that the DA experiment shows relatively larger bias compared to no DA experiment. This is out of our expectation. We are still working on the potential reason for that. Also, with this utility available, we also plan to compare their angstrom exponents, and this will give us some idea about their aerosol computation difference. This slide compared temporally average AOD against analysis from NASA on the left and the ECMWF on the right. The top panel figures are for no DA 6-hour forecast. The bottom two figures are for the D analysis. So you can see that compared to no DA 6-hour forecast, the D analysis is able to efficiently reduce the bias almost globally, except for the regions close to the Arctic. This is because during this evaluation period, there is a very large wildfire event in Siberia, and we don't have the AOD observations at our regions, so the D is not able to create efficient correction over our regions. In the past 2 months, there have been several severe wildfire events in the US. In this slide, we compared the DA and no DA experiments with the analysis from NASA and ECMWF in an Oregon wildfire events for the period of August 3rd to 9th. The animation shows the AOD evolution. So you can see that the DA analysis shows a very good agreement with the analysis from NASA and ECMWF. And it's also need to mention that our DA run is computation much cheaper compared to the NASA and ECMWF run. So the results are pretty encouraging. To understand how the two-dimensional AOD is going to affect the three-dimensional aerosol concentrations, we further compared regional average aerosol mix ratio profiles with NASA and ECMWF analysis over different regions. So as you can see in here, for the total carbonaceous aerosol species over CONUS and sulfate aerosol species at East Asia, we can see that the D background and analysis in general shows a better agreement with NASA and ECMWF analysis compared to the no DA experiment. However, for CSOT and dust, the results between no DA and DA are kind of mixed. We further look at the time series plot. It shows that the emission factors of dust and CSOT are kind of too large, which may be the reason why we see the mixed results for the DA and no DA experiment, and we are still working on that. Here is a summary. JEDI-based aerosol data assimilation system has been developed to improve aerosol forecasting in NOAA's GAPS aerosol model. To deal with the model AOD bias and background error ensemble spread deficiency, we developed a stochastic perturbed emission method. Our recent cyclic near real-time experiments in July and August 2021 show that assimilation of AOD retrievals is able to improve simulated AOD aerosol concentration by comparing with independent AOD retrievals and NASA and ECMWF analysis. We also realized that further tuning of emission scaling factors are needed, which will help us to understand and address the bias issue in the DA experiment and compared to no DA experiment, and improve the performance of the system. A lot of developments are still ongoing in JEDI, such as the variational bias correction and observation thinning. When available, we will further incorporate these capabilities in our system and investigate their performance. And also, we seek strategies of further increasing the ensemble spread and more accurately estimating VIIRS AOD errors.